Welcome to Lecture 10. This is on Section 7.1, and we're talking integration techniques here in Chapter 7. So this is 7.1, integration by parts. So remember that in use substitution, when we did use substitution, that was undoing the chain rule, right? So the next rule that we want to undo is our product rule. And so just recall that the product rule tells us this. If we have f times g prime, that's f prime g plus f g prime. And I like to kind of write it without the x's just so I can kind of see what's going on. So f times g prime is f prime g plus f g prime. And actually I'm going to write it, no, we'll stick with f g prime. That's fine. Okay. Now, one of the things we want to do is we want to undo this. So the opposite of taking the derivative would be taking the integral. So if we take the integral of each piece, and these are all functions of x, so we're integrating with respect to x, then the only one of these that we can simplify is this first one. The integral and the derivative undo one another, a la the fundamental theorem of calculus. So this just becomes f times g. Okay, but we typically aren't seeing questions where we're just going to take the sum of two things and take the antiderivative or take the integral. So what we're going to do is we're going to rearrange this a little bit. And I am going to subtract off this last one, this one right here. So we're going to subtract this one. And if we do that, actually we're not. Scratch that. We're going to subtract this one from both sides. So if we subtract that from both sides, then on the right-hand side, I just have the integral of f g prime dx. And that's equal to f times g minus the integral of f prime g dx. And I'm just going to flip them around. So the integral of f times g prime dx is equal to f times g minus the integral of f prime g dx. Okay, so now we can kind of use this as a formula. If we focus on problems that look like this, where you have two functions being multiplied together, where one we think of as a function f, and one is the derivative of another function, then we can undo that or take the integral by using this formula. Okay, now in order to align it with the way that we did our u sub, we're going to substitute u equals f of x and v equals g of x. Now keep in mind, little side note here, that if you have that u is equal to f of x, that means that du, the derivative, is f prime of x dx. And if v is g of x, then dv is g prime of x dx. So anytime I see g prime of x dx or f prime of x dx, we know that that's dv and du. So if I use that to make the substitution here, then this becomes the integral of u, because f is u, and g prime dx is just our dv, is equal to f and g are just u and v, so this is u times v, minus the integral of g, which is v, and f prime dx is our du. Okay, and so here is our formula for what we call integration by parts. Okay. You can memorize that if you like. I don't, because I set it up in a certain way so that I can see it visually, and then I can remember what to do with what I've got, and I don't have to memorize. Okay. Let's take a look at example 1. So I've got two functions multiplied together. I've got the yellow one is my x, and then I have the cosine x dx. Okay. I'm going to go ahead and choose my u as the x, and that means everything else is my dv. So dv here is the cosine of x dx. Notice that the dx always goes with the dv or the du, depending on which one you're working with. Okay, so if I have u equals x, then I'm going to need du, which is the derivative, and the derivative of x is dx. Now in blue here, we have dv equals cosine x. Sorry about that. And I want v. And v is the antiderivative of dv, so the antiderivative of cosine is sine x. Notice that when I take the antiderivative, I lose the dx notation. Okay, so from here, I want to follow the formula. And the formula tells me that the integral of u dv, which is exactly what I have here, is u times v. And u times v is this diagonal. So I just think about, let's multiply along the diagonal. And that's going to give me x sine x. And then it's minus the integral of v du, which is these two multiplied together. So I just think of it visually as multiply along the diagonal minus the integral of the two bottom ones. So this is the integral of sine x dx. Okay, and then we do have to go ahead and find that second integral. So the antiderivative of sine x is negative cosine x. And that gives us x sine x plus cosine x. And because this is an indefinite integral, we don't have boundaries, we need to add on our plus c at the end. Okay, and so that is how our integration by parts works. Let's look at another example. Notice, there's a little note here, that u, when we take the derivative of u, in this case, by choosing x as our du is simpler, right? When you take polynomials and take the derivative, there's less stuff going on. The powers are lower, terms go away, that kind of thing. Notice that with cosine, that doesn't happen. When you take the derivative or antiderivative of cosine, you get sine, and that's about as complicated as cosine. So we're typically choosing our u as something that's going to get simpler as we differentiate. Now, of course, there are exceptions to that rule, and I'm going to show you that one here. So in example 2, we've got a function x times a function ln of x. And I don't want to put those together with the dx, okay? Now, typically, where we would start is let's make our u our x. And then du is dx. And that makes dv the natural log of x. And then we want to find the antiderivative of the natural log of x. Except we don't know what that is, right? We know the derivative of natural log x is 1 over x, but we don't know what the antiderivative of ln x is. So this isn't going to work. Scratch that. Instead, we're going to have to make the choice the other way around. Because we don't know the antiderivative of ln x, that has to be our u. So u is ln x, which makes du 1 over x dx. Then I take what's left, the x and the dx, and that becomes my dv. Antiderivative here, antiderivative of x is 1/2 x squared. All right, so when I go to put together my integration by parts, I multiply along the diagonal. So I'm going to get 1/2 x squared ln x. Now this is a definite integral and we do have boundaries, so we're going to evaluate that from 1 to e, minus the integral from 1 to e of these two multiplied together. So 1 over x times 1/2 x squared dx. That gives me 1/2 x squared ln x, evaluated from 1 to e. And here I'm taking the integral from 1 to e of 1/2 x dx. If you want, you can bring that 1/2 out in front of the integral, but you don't have to. And this is 1/2 x squared ln of x from 1 to e. Antiderivative here is going to be negative 1/4 x squared from 1 to e. And then we can go ahead and plug in our boundaries. So I'm going to put in the e to both of them first. Actually, it doesn't matter how you want to do it. If we plug in the e, we get 1/2 e squared ln of e minus 1/2 times the ln of 1 minus 1/4 times, when you plug in to the x squared, that's e squared minus 1. Okay, what I know here is that the ln of e is just 1, sorry, and ln of 0 is 0. So that tells me that I have 1/2 e squared, the second term is 0, minus 1/4 e squared plus 1/4. And that reduces all the way to 1/4 e squared plus 1/4. And that's my final answer for example 2. Okay, so that one's just a little bit trickier because we have to choose our ln as our u. For example 3. All right, so sometimes we have to use the formula more than once. Here's an example where that shows up. So again, I've got two functions being multiplied together. I've got an x squared and an e to the x. I'm going to choose my u to be the x squared. That means my du is 2x dx. Then my dv is going to be e to the x dx, which works out nicely because the antiderivative of e to the x is e to the x. Now I put this all together. So this is the diagonal, so x squared e to the x, minus the integral of these two, so 2x e to the x dx. Okay, perfect. Now I'm working with the integral of 2x e to the x. But guess what? Here we go again. Two functions multiplied together. So let's use by parts again. Now what I want to make sure I do is I want to make sure I make the same decisions for u and dv. If I make the opposite choice and make my u e to the x and my dv the x, then I'm going to go backwards and head right back to where I started. Okay, so I don't want to undo the by parts that I already did. So I'm going to be consistent with my choices. So that means my u is going to be the 2x, and the du then is just 2 dx. And the dv is the e to the x dx, which means my v is e to the x. Okay, so I've got the x squared e to the x from above, minus big parentheses, because what I have coming next is two things being subtracted. And now I have u times v, so 2x e to the x minus the integral of the 2 across the bottom, so 2 e to the x dx. So I've got x squared e to the x, distribute the negative, so minus 2x e to the x, plus the antiderivative of 2e to the x. Antiderivative of e to the x is e to the x, so this is just 2e to the x. Add on my plus c because it's an indefinite integral. Okay, so in this case, we used integration by parts twice. If I had an x cubed, I'd need integration by parts 3 times. Okay, now what by parts allows us to do is to integrate things that we can't always integrate. So I said above that we didn't know the antiderivative of ln x. I can actually use integration by parts to get it. Same thing for arctangent, and here's how it works. So in this case, if I think about choosing arctan as my u or my dv, I don't know the integral of arctan or the antiderivative of arctan. That's why we're doing this. So I can't make that my v, so I'm going to have to make it my u. So I'm going to make my u arctan x. That means its derivative is 1 over 1 plus x squared dx. Then the only thing left to be my dv is the dx. Antiderivative of v. Sorry, v is the antiderivative here. And we're going to pretend there's a 1 there because there is. There's an unwritten 1 right there. And so we want the antiderivative of that, which is just x. So my v is going to be x. And that tells me that I'm going to have the integral of these two multiplied together. So x, arctan x, minus the integral of x over 1 plus x squared dx. Okay, now we move to this part. So now we need to integrate this. So I have an x on the top and a 1 plus x squared on the bottom. This is going to be a u sub. I'm going to u sub for the denominator. Then du is 2x dx, but I don't have the 2. So I'm going to make it 1/2 du, divide both sides by 2. And that means I have x arctan x minus the integral of the 1 over 1 plus x squared becomes 1 over u. And the x dx becomes, 1/2 du. Okay, antiderivative 1 over u is ln. So this is the natural log of u, so 1/2 the natural log absolute value of u plus a constant. This is indefinite, so we get the plus c. And then lastly, I got to plug in that u. Now, don't confuse the u from by parts with the u for substitution. Okay, if you need a different letter, make a substitution for r or s or something of that nature. This becomes x, arctan x, minus 1/2 the natural log of 1 plus x squared, plus a constant. Okay. So no wonder we don't know what the antiderivative of arctan x is. It's a little bit complicated. We can do exactly the same thing for ln x. So in the same way, I make my u the ln x because I don't know its antiderivative. That means my dv is the dx. So my du is 1 over x dx, and my v is just x. So then when we put this together, this is along the diagonal x ln x minus the integral of 1 over x times x dx. And that simplifies to just the integral of dx, which is a 1, and the antiderivative of 1 is x, so minus x, and tack on our plus c because it's an indefinite integral. And that's how we find the antiderivative of ln x. Lastly, there's one more that gets a little bit tricky with integration by parts, and that happens when you have e to the x and sines or cosines. And the reason for that is that with e to the x, the derivative and antiderivative are exactly the same. So e to the x isn't going to change from one step to the next. And our sines and cosines, if we take derivatives or antiderivatives over and over again, it just bounces back between sine and cosine. So you have this kind of cyclic thing happening here. Okay, and so how we handle that is we're going to do it twice and then collect our integrals. And I'll show you what that means. Okay, so it does not matter whether we choose our sine x or our e to the x to be our u. Personally, I like to choose my u to be my trig function. And the reason I do that is just because for me, it's easier to keep track of what's negative if I'm taking derivatives than if I'm taking antiderivatives. And that's a personal preference. If you want to switch these around, you absolutely can. So I'm going to choose u to be sine and my dv to be e to the x dx. That makes du cosine x. And it makes v e to the x. Oops, I need a dx. Okay, so integration by parts tells me that this is along the diagonal. We have e to the x sine x minus the integral across the bottom of e to the x cosine x dx. Notice that my new integral looks identical to the old one, except that it's cosine now, okay? So we're going to do it again, okay? And that means that we're going to be consistent. So if I chose the trig function to be my u prior, I'm going to make the cosine my u this time as well. And then my dv is e to the x dx. So then I have that du is negative sine x dx, and my v is e to the x. Okay, so from above, I have e to the x sine x minus big bracket because lots of stuff come in. Now, for this integral right here, I'm using integration by parts using the stuff to the right. So along the diagonal, I have e to the x cosine x minus the integral of negative e to the x sine x dx. And I'm going to go ahead and I'm going to distribute and simplify here. So this is e to the sine x minus e to the x cosine x. All right, now we got to make sure we get our negatives right. So this negative and this negative becomes positive, but this negative gets distributed. So it's minus the integral of e to the x sine x dx. Okay. Okay, now notice where we are. This is exactly the same as this, which is where I started, okay? And what that means is that I have this statement. So the integral that I started with, e to the x sine x dx, is equal to e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. notice that these two things are the same thing. Okay. What I'm going to do, if those were variables and I was solving for that, I would move them to the same side. So what I'm going to do is I'm going to add the integral of e to the x sine x dx to both sides. When I do that, I have 2 integral of e to the x sine x dx is equal to, these two cancel, and I'm left with just e to the x sine x minus e to the x cosine x. What I'm trying to find is this integral right here. So in order to get that by itself, I just have to divide by 2. So if we divide by 2, it tells me the integral of e to the x sine x and dx is equal to 1/2 e to the x sine x minus e to the x cosine x. If you want to distribute that, you can. But that is my final answer, except I got to add a plus c. So in this case, and it's only the case when you have an e times a sine or a cosine, we use integration by parts twice, and we get back exactly what we started with. We add that to the other side and solve for the integral. So that one's a little bit tricky.